I'm starting the AI lectures at the university without just a few concepts of theory. I think that it's needed in order to know where we are and why we are here. And this is the history just summarized in 6 bullet points. To be honest, this is not the first time that AI is taking value, not only in the academical area, also in business. But AI was born in the 50s, so a lot of time ago, and we have suffered 2 different winters. The first winter happened in the 70s. And why happened this winter? Well, the problem there was that people was not power computing enough in order to run the deep learning, the neural networks that they were discovering at this moment, the huge algorithms that they were using at this moment. They were working with huge computers, but the old ones, and they didn't have the power computing that they required in order to process and in order to shift and to boost AI. So for the reason, well, once that happens at this moment. But in the 80s, we were talking about personal computers. And the 80s, thanks to the personal computers, power computing was more democratized around the world. So it seems that the AI can have more room for expansion. For the reason in the 80s, we have a boom. But again, in the 90s, we have the second winter. And why was coming this second winter? Could you imagine which is the problem of this winter? Well, people needed more storage, and they couldn't have the required storage in order to manage data in the amount of data that AI needs. So once we have solved the problem of the storage with cloud, with bigger drive systems and so on, AI now is it's accelerating, is speeding up a lot, because that we have solved the two main problems: power computing and storage. And maybe these concepts are bringing a very good definition of AI. Here you can read many different definitions about AI. I like to present my own version of the AI definition. My own version says that AI is like a cocktail made with 3 main ingredients. One ingredient is power computing, as we saw in the winter. The other ingredient is algorithms. So we have to transform this algorithm, this software, in some activity, in some actions. And the third ingredient is maths. With math, software, and power computing, you can have AI. And this is the 3 ingredients of this cocktail. But if you want to have a good cocktail, you need a secret sauce. And the secret sauce of this cocktail is data. So 3 main ingredients to have AI, 1 secret sauce to have good cocktail, good AI, data, good data. So remember the Alcoa Plus principle that we were talking about yesterday. So data must be compliant if it must be used in GXP or regulated environments for life science. And I like this sentence that one of the fathers of AI mentioned in 2004. Tim Menzies, this is one of the fathers of AI, he said that AI in 2004, he said that AI won't be in the future a hype anymore. He forecasted that AI will be a commodity in the new society. That happened in 2004. And I think that this vision has been accomplished, because nowadays we can, personally, we cannot live without AI, because AI is everywhere. Well, let me introduce different concepts before to go to the details, but I think that it's important to know the difference between machine learning and other branch of AI. Machine learning is a branch or is a field of the artificial intelligence where we are using statistical techniques. This is important, statistical techniques, where we can progressively improve the performance of a specific algorithm, and the algorithm can learn for something that was not programmed to do so. This is amazing. So it seems that when you are creating software, the software is made for something, for some intended use. With machine learning and using statistics, this algorithm can do something that was not intended for since the beginning. And the difference with machine learning and deep learning is that deep learning can grow up in a scalable way. This is one of the main difference. So deep learning is based by neural networks. There are different kinds of neural networks. There are convolutional, there are systematic. There are many kinds of neural networks. But the most important thing about how to consider neural networks is like something, is a system that is able to learn scalable. So when you have machine learning, the scalability of this algorithm is the one that you have defined at the beginning. But with deep learning, you can scale up this way to learn from 0 to infinite, practically to infinite. And this is why we introduced the reinforcement learning. Well, here you have I'm not a fan or supporter of games, but this is for all of you that you have kids, you have children, probably these names will sound familiar for you. This is the different games, video games that they are working nowadays. Well, the thing is that, as you can see, the level of AI that they are using, the deep learning, they are, well, increasing a lot. So here in this line, maybe the Hero game is familiar for you. The Hero one was the first game that was at the same level than humans thinking. From this line to going to up, we're talking about the same level of human learning curve for games. Okay, so games are not only the hardware, the PlayStation box that you are using. The games are using AI algorithms, deep learning algorithms, in order to learn about the way that you are playing the game. Well, could you see that nowadays there are really really amazing percentage about how much quicker they are learning than humans. What really is AI? Do you know this expression? Do you know this formula? This is the maximum heart rate expression that probably if we have doctors between the audience, they can recognize this expression. This is in average how you can calculate your maximum heart rate. Well, if you subtract 220 minus your age, you can have this maximum heart rate. Okay, well, how the experts arrive this expression? Because here, if you see that from a scientific perspective, we see a magnitude, maximum heart rate, that doesn't have the same unit of measures that age. And we're subtracting a number to a unit of measure transforming into age. So this is a little bit weird from a scientific perspective to understand that. Why? Because this expression is a model of a reality that is based on statistical approaches in a aggregation of many data that we can bring from patients around the world, patients, races, countries, ages, well, the diversity of the patients are at the end bringing this expression that is not explaining the why of the physics behind the reality that we are interpreting. This is just aggregating statistically a concept. So this is a very good example of what really is AI. AI is a model that is able to represent something mathematically and that can be used systematically in order to bring a specific knowledge. I like this expression like for the similarity. And let me go deeply because we are establishing the foundation of AI. It's important to know what really is AI in order to don't have confusion later. Do you remember when we were studying classical mechanics? We were, for example, in order to identify, in order to measure what happens inside a valve, we had a lot of formulas describing the analytics of this system, this mechanical system, in order to identify the speed, the volume, the capacity, and the frictions, and so on. But you can do the same from analytics using the statistical mechanics. So which is the problem of the classical mechanics? The problem is that you can have the exact and with a lot of precision analytical expression describing the theory, describing the nature of the object that you are describing. So you can understand using these analytical expressions which kind of magnitudes are involved in the explanation of the problem. With AI, is the same that we have in statistical mechanics. We cannot predict efficiently where each particle will be in the next second. So it's like a chaotic system. But with AI, we can have an idea of the full system working together, because we have multidimensionals, multivariables interacting in a complex way between them, and we cannot exactly foresee or envision or calculate individually which is the next position the next time, but we can measure the temperature, a new observable of the system. That is very good. It's a very good similarity with AI. Okay, AI requires the data coming from every single particle in order to measure the temperature, and we will be very accurate depending on the data that we are using. With classical mechanics, maybe you can do the same, but you're going to need a lot of equations in order to include all the parameters, all the variables inside the system. Please try to keep this picture, because this picture is the differentiation between how we can tackle a problem from an AI perspective, how we can tackle the same problem from a classical perspective. And a new way to understand AI. Could you see all those graphics? All those distribution of particles, all of them, they have the same correlation, let me say, the same standard deviation, practically the same X mean distribution, the same Y mean distribution, except the third decimal figure. But so from a statistical perspective, all of these graphics, all of this distribution of dots could be considered the same if we talk about just 2 dimensions. But from an AI perspective, all of them, they are different, because we are including the human knowledge. We are including the human perspective. We are able to extract something new, something emergent from a classical distribution. This is how AI works. So when we talk about the AI, we're doing something more than just working with multivariable models. We are able to emerge new knowledge coming from the basics that statistics cannot do. Okay, so this graphic, or these concepts are really, really good in order to understand what really AI is. And I remember the sentence of Tim Menzies, one of the fathers of the AI. We can have amazing applications today that they can be considered as commodities. For example, when you were able to talk to your smartphone, and the smartphone is able to identify what you were describing, you were talking in words, that is made by AI. The difference or the thing is that this kind of simple, let me say simple applications, they are using a very complex neural networks. In this case, they are using usually recurrent neural networks. When you are identifying your face in your smartphone, when you are passing the airport, and the airport is counting how many people there are passing through the control systems, all these kind of things, they are using recurrent neural networks, and that means that they are able to store previous information, previous knowledge, in order to accumulate this knowledge for the next iteration. this is how the brain works. So we are learning because we are able to accumulate this knowledge that we are experimenting in our cells, in our neurons, and we are using this stored knowledge for the following iterations or for the following interactions. So this is the basics of the recurrent neural networks, and this is how this kind of systems they work. Well, another kind of common use in the industry is the convolutional neural networks that they are being used, for example, in self-autonomous car drivers. Then they are using this kind of convolutional neural networks architecture in order to split pictures, images in pixels, and they are able to create shapes because the difference between the colors of the pixels, the size of the colors, the areas, and so on. Okay, so this is another example of commodity nowadays. So Tim Menzies was really good envisioning the future. And this is another commodity. We are talking about AlphaGo Zero as a game, but this is applied nowadays to meteorological concepts. So this is how nowadays recurrent neural networks and convolutional neural networks, they are able to learn in a very fast way. So the learning curve of this kind of systems, they are so huge because the power computing that we have nowadays. So here, this is the example of the AlphaGo. I don't know if you are fan or not supporter of this game, but it's very famous. And this is how many days the AlphaGo program working with Google spent in order to bet the adversary, the contrincant. Well, do you remember that we have showed several times the Moore's law? Well, AI is impacting nowadays, and this is coming from Gartner, which was the vision of the hype cycle of emerging technologies during this year. Well, the thing is that AI is not a hype anymore. So AI was a hype several years ago in the past, but nowadays it's not a hype. It's something that we have assumed and is part of our industry. This is very important. I think that I encourage you to follow this Gartner curve, because they are publishing these statistics every year, and you can see the evolution, how they are close to the forecasting. It's important to mention that AI is around many sectors, even pharmaceutical industry and even medical value chain. And nowadays, in terms of AI, we're talking about a hype like AI augmented software engineering. For example, Google is working in a program where you can develop software without humans. Software can be developed by AI. So you say, for example, I need an application that takes the values, the data coming from this sensor, and that presents the data in a graphic, in a linear graphic with the prediction for next year. So just talking, you can create your own application. This is the hype nowadays, how we can augment AI in order to evolve. But AI itself is not a hype anymore. This is important because that means that AI must be already in our lives and in our jobs. Otherwise, we will be old-fashioned, or we will not update it. Well, some additional concepts, understanding AI. I mentioned the three secret ingredients for AI and the secret sauce. Well, once you have in your mind very clearly identified these concepts, it's important to go deeply and to explain the elements that we need in order to work with AI. The first one is data. Data, if we don't have good data, we won't have good AI models. So there is a principle in AI that says garbage in, garbage out. And this is a reality. So for this reason, when we were talking during all the sessions about digitalization, about data, and this concept has been appeared several times, we always need to talk about good data. Remember, And data means not only to have volume or velocity or variety, means validity and means veracity. This is so, so crucial. So we need to have data that explains the problem or that we think that could explain the problem, because we have in AI different techniques to identify if the data that we have is good enough to describe the problem and to run AI. Well, once we have data that we will use to train the algorithms and to test the algorithm, so we need to split data in between training and testing to verify if it is good or not. We will have the mathematical procedure, the software. The software is the algorithms. We have hundreds, thousands of AI algorithms. All of them, they are, or many algorithms, they are open source that can be used for free. So science is free. Science is belonging to humanity. And we have every day, in average, 75 new patented algorithms. 75 new patented algorithms in average. So it's not possible to have them, all of them in mind. But we have probably an algorithm for everything. We have models. When you train the algorithms and afterward you test the training with the data test, and you have a model, you have the mathematical system, the emulation, the virtual thing, the digital twin inside this model. This is so, so important, because you can have a batch production and operation of your drug manufacturing, a biosystem, a pattern for patients that they have specific characteristics, how they are answering, how they are reacting in front of a pacemaker or in front of a insulin pump. So the model is a complex system that represents the reality coming from the data. And you can have outcomes from this model. Here I'm writing prediction, but please don't think only in predictions. Think in recommendations, in pattern recognitions, in clusterings, in image recognition, in sound recognition. So the outcome of AI could be a lot of things. And this, please don't forget that, never. We cannot rely on a model without the corresponding evaluation. So we will talk about that today. This topic is so, so crucial. We cannot use AI in our context, in our life science context, without an evaluation of the AI. And that should be done in real time. Every time that we do a prediction, every time that we run an AI model, we need to evaluate how much good is it, because otherwise we need to establish a policy in order to renew the AI model, in order to create a new one with new characteristics, new variables in other conditions. And this is the real life of AI. Do you remember the data is the secret sauce of this cocktail? Well, let me explain you, let me share with you my pain, or the pain of all the data scientists. The pain of data scientists is that we are investing the 80% of our time just preparing data. Because in most of the cases that we are analyzing, we are not working with data coming from the fourth industrial revolution. We are at the beginning, we are trying to adapt the pharmaceutical industry or the health sector to the new evolution. And we have to work in the classical way. So if you are preparing your facility, your systems, in order to understand, in order to implement the good strategy for the future, please consider that you cannot be efficient if you dedicate the 80% of your time just cleaning up data, just preparing data, just doing all these kind of things that you need in the data before to apply AI. So we cannot spend this time continuously. We cannot transform AI in a craft. We have to industrialize AI. And this is the key when we talk about AI, a fourth industrial revolution. We cannot work manually like expert craft, making nice objects with wood. No, please. We're talking about fourth industrial revolution. We need to scale up. We have to industrialize this AI without to invest 80% of our time every time that we apply AI. Okay, so this is crucial. And how we can solve this problem? Well, the problem is solved when you have a good strategy in the technology that you're using in order to get data, to don't use silos. Again, one of the main reasons about why we cannot expand AI is because you have silos of data. We have silos of data, and we need to break these silos, put all data together, put all the data aligned in the time. What happens if I have, for example, imagine this case. What happens if you want to apply AI, AI in real time in your process, in your line of manufacturing processes, when you buy a reactor, when you have a measurement of this variable pH at this moment, density later, 1 second later, humidity 1 second later, the agitator speed 1 second later. How we can do big data, how we can do AI with this big data? Because we cannot put together at the same line. We need to create this kind of alignment, time alignment. Well, that must be foreseen, must be integrated in the strategy. Otherwise, you will need a lot of legion of data scientists working for you, always trying to align data and preparing the data and sending the data by using a pen drive or by email. No? So please try to generate clean data at the source level. As much cleaner is the data, faster you can go using AI, and most benefit you can get. This is so important because there are many pilots that they have been successful implemented that they cannot be scalable, and the pilots has been finished in the pilot, in the MVP, in the minimum viable product, but they cannot scale up that because data is not ready to be scaled. Remember, we have talked that, we mentioned that several times. Data is the fuel, is the petrol of this digitalization industry. So please create good data since the beginning with the right metadata around every single value, always well established, without well governance, without the risk of to be violated, and so on. Once you can rely on this data, you can apply AI very easily. This is believe me, this is a very good advice. So please think on that, because you can save, you can, this is the difference between good implementation and opportunistic implementation. And here you have the proof. Do you know this guy? I'm a fan of this guy. This is the CEO of Novartis. He's a young guy that is leading Novartis towards the new generation. Well, in 2018, sorry, if you go to the Forbes interview, this is in the presentation, so probably you will have access. You can read in this Forbes interview how much difficult it was for Novartis to work with big data, because they spend a lot of time just preparing the data. So well, that was a huge and costly process before to go AI. Could you see? So AI, but first data. This is nothing. This is not it's not my sentence. It's a sentence coming from this guy, and not only a sentence. Is the reality that this guy was living at Novartis. Okay, so data preparation. So if you can prepare data at the origin and in the storage, that could save a lot of time. And this is making the difference between success or failure. Really, yeah, is true. And yesterday we talked about Alcoa. So today I don't want to spend more time in the Alcoa concept. There are a lot of literature coming from the ICH, the International Committee of Harmonization. Also in the WHO, they have a specific chapter dedicated to the Alcoa and also to the FDA. But I would like to highlight that there another principle the fair data that is coming is older than the Alcoa, that is the main guidance, the commandments that data scientists are applying since the beginning of AI. The fair principle means that your data must be always findable, must be accessible, must be interoperable. So please don't create silos, and must be reusable. So this fair principle is, there is a important parallelism between this data science principle and the Alcoa ones. So we can create a parallelism. If you want, we can dedicate some time tomorrow or maybe another day about how we can establish the foundation of our data for life science, for medical purposes, for drug manufacturing purposes, in order to be compliant, but not only considering the Alcoa. The Alcoa is from the regulatory perspective, but from a functional perspective, from a efficient perspective, you should apply also the FAIR principle of data. So here you have another very good advice if you want to take advantage in your business of data in life science. Of course, if you are working in other sectors, I don't know, in gamers or in fintech or I don't know, that is not necessary. But we are serving to patients, and this is so crucial. We have to be professional with that. And another topic is be aware of outliers. In classical statistics, if we apply 2 dimensions, and this is the classical way to proceed, at least in many companies in Europe, and also in some company in the US. This is my experience. So I saw a lot of submissions for drug submissions to the health authorities when the science teams, the research teams, they were applying linear approaches to behaviors that were not not really linear. And even more, they were trying to explain everything in 2 dimensions, and this is not the reality. Well, in classical statistics, when you find an outlier, usually you delete the outlier because you identify that this is not normal. So this is something that we have to delete. And in classical statistics, we do that. Please beware of outliers when we talk about AI. Maybe the outliers contains the information that you are looking for. So this is another way to understand the AI in regards of classical statistics. We have a different vision. Every single point, every single data counts on AI if data is good, and an outlier is good if it is not an aberrant. For example, we have a project where you have to differentiate the calibration process from the ongoing process, the manufacturing process. So calibration, usually they have this kind of aberrant values, of course. But if you have outliers, because the data is good, you have not to remove them from the sample. Please consider them because maybe you are looking or you are looking for a root cause that is in this outlier. Okay, very important. Well, do remember garbage in, garbage out. The right data, and I think that Urban mentioned that yesterday. We need good data in order to have good AI. I'm insisting because, believe me, it's really, really important. And here is when we bring the idea of big data. So if we have only a few dots, only the red dots, and we try to create some model that explains these red dots, we will have the green line. But imagine that the reality is more complex, like in a biosystem that is interacting with sugar or with glucose or whatever. I saw many graphicals in bioreactors where the graphical is so complex and people is trying to smooth the graphic with a green line. No? So we are losing a lot of information if we don't use more data. And the other thing, this is another important concept in AI, no free lunch. No free lunch means that with only one algorithm, you cannot solve all the problems. So we have many algorithms that can be used, but with only one, you cannot solve everything. So you have to make a deep study on what do you want to solve, which is the digital twin that you want to create. And probably, and I'm pretty sure that if you are creating a digital twin of a process, you're going to need more than one algorithm. For example, if you look for the CPV of the future, it's a project that we are leading with the Product Quality Research Institute. In this project, we created a digital twin for a bioreaction. Well, the thing is that this paper will be published, will be available in the PDA journal on January next year. If you're interested in that, it's a scientific paper for free, where we are demonstrating how AI can bring value for continued process verification for CPV in drug manufacturing. Well, the outcome or the takeaway from this paper, there are many, but one of them is that we needed one algorithm per hour, coming back, one model per hour using more than one algorithm per hour in order to digitalize one bioreactor process, specifically the Pichia pastoris fermentation, in order to produce a lipas that was used for a drug process. So we spent 24 hours in order to get the batch, the final product, and we needed more than one algorithm and one model per hour in order to create this digital twin of the process. So this is the reality. With only one model, we cannot solve a problem. Probably you have to work with more than one forest or models that you can see in this graphic in order to be more accurate. For example, what happens if I'm running my packaging line? This is a real problem in a Nordic company, that they are working with a packaging line that is so critical because they are delivering some insulin products to the world. Well, they realized that they had a problem depending on the season. What happens if you are living in a very humidity country where packaging cartons are affected by the humidity, and you are warehousing, you're storing these cartons at the warehouse? Well, we need an AI model to avoid downtimes depending on the season, depending on the hour of the time, depending on the shift. If we are producing in the morning, is different than if we are producing in the night. So this is very important. Please, if you are considering applying AI to your job, you have to prepare your infrastructure, your procedures, your quality, because you are going to need more than one model, and probably more than one algorithm to digitalize, to modelize your reality. And well, this is the difference between supervised and unsupervised. And now I have some examples about how to differentiate supervised and unsupervised, but let me explain very briefly. Supervised means that you have tools in order to say to the model if that is good or not good, if the output that you are getting from the model is right or not right. And unsupervised means that the algorithm is discovering by itself hidden structures. What does it mean unsupervised? Well, let me try with an example, which is the exercise that we're going to do now. Now I'm going to drag and drop, I will upload an image that I have in my laptop, and in a unsupervised way, I will try to get feedback coming from an AI system that is analyzing the image from me. So let me go to my desktop, and I will take a picture that I like a lot because this is my hobby. I will take a picture that is all the subatomic particles that has been identified in physics, okay? And I will try that this Google system analyzed this table of particles, so the bosons, the fermions, the electrons, and so on. Okay, well, in a non-supervised way, this AI algorithm is able to say that This picture of particles, of electronic and subatomic particles, they recognize that this is found. This is it's a found, it's a source found in 82%. It's categorizing this picture as a parallel, something parallel in 70%. Pattern is able to say that this is technology. This is a little bit wrong because it's not technology, it's science. It's recognizing symmetry, electric blue, machine, science. Could you see? Science is not in the top, and it's a particle is totally science. Circle, rectangle. So in a non-supervised way, this analyzer of Google is not working properly with this picture. So probably it's because people is not uploading this kind of pictures. But if you try to do the same example, the same exercise, using faces, using pictures of your family or surroundings in the mountain, in the beach, you will see that the analyzer is very good because the system has learned by this kind of common pictures. If you go to save, so the system at least is able to recognize that it's not adult toxic, it's not a spoof, it's not medical, it's not generating violence. Well, at least that is good. Okay, that is non-supervised AI. I hope that that is clarifying a little bit the concept. And depending on which is your problem, you should use one way or another one. For example, when you have, imagine that you have a list of batches that you have produced, good batches and bad batches, and you know which of them they were good and which of them they were not good. In this case, the best way to proceed is work with a supervised algorithm in order to reinforce the algorithms and the model, because you know which batches were good or not. But if you don't know, for example, how to classify a problem with several use cases, you can use k-means in order to create clusters. This is a very good tool. If you want to find anomalies, but you don't know which of them they are anomalies because you are working in multidimensional spaces, please use the isolation forest. This algorithm is a very, very good unsupervised algorithm that works very well with just a few data and able to identify anomalies just with multiple dimensions, just in with a few data. And well, this is the life in the AI. We have to split the AI in these two worlds. In one hand, we have the algorithms, the data that we have used in order to train the algorithms. We can have some tuning, and well, we have to work with algorithms. In pharma, we have to qualify algorithms. In pharma, we need to calibrate our algorithms independently of if this algorithm has been created specifically for some specific purpose or not. And the model that is the outcome of the algorithm has to follow another life, because the model is used in the real floor. So you can create an algorithm in the desktop in research, but the model will work in the floor. So you have to validate the model. You have to qualify the algorithms in life science. So this differentiation is so crucial in order to apply AI in life science. And the data that we use is really important. So let me make another example on real life. In this canvas, I can write a number, and if I write the number well, I can see how this number is interpreted by the machine. Number 3. Let me try with 2. 2. What happens if I do something like that? 4. It's not a 4, it's a 7. Which is the problem here? The machine that the Keras model that we are using here was not trained with this 7. The 7 that this machine was trained with was something like that. Or neither that, because it's interpreting a 2. So I don't know how I can write better a 7, maybe, this one. So could you see the data that we are using, the samples that we are using in order to train the models are so crucial in order to avoid problems. The data that we use for the training model must be kept with the algorithms if we use that for GXP purposes for life science, because we need to keep traceability. We need to transform the classical black box AI way into a transparent box. So regulators, the health authorities, they cannot accept a black box that you are using in order to predict why you change this parameter by this other one in order to improve your yield or the quality of the product. They won't accept a black box. They only will accept a transparent box where you are able to describe, explain, and keep full traceability of everything starting from data. So, or if I'm training this model with these figures, I have to store all of them. And this is how a neural network works. So this is the same model that I was using in the Kanban in order to recognize numbers. Every single pixel has two potential values. This is not quantum computing. We're talking about classic computing. Each pixel has 0 or 1. Well, could you see in the 3, we have 1s in the black areas, 0s in the white ones. So we can have as many neurons. Each neuron, each circle that you can see in the input corresponds to a pixel. Okay, so this first pixel is represented by this neuron. And this neuron can have only 2 potential values, 0 or 1. Well, when you train a neural network, at the end, you can have many pixels of input, as many pixels as we have in this graphic, 784 pixels. And the output is the 10 numbers that we can predict, from 0 to 9. Okay, and in the middle, you can put as many hidden layers as you need. This is the scalability. So you can perform better, you can gain accuracy, including more hidden layers, taking into account that you have to take care of the overfitting. But this is more or less a classical deep learning network. Okay, this is more or less how it works. So as many use cases you can make in the input, you can fit the neural networks with different 7s, different 4s, different 3s. The neural network can run with more accuracy. And this is an example that I would like to bring to you. There is a old statistical formula, the Bayesian network, sorry, the Bayesian formula. Do you remember the Bayes law? The Bayes law is the conditional probability. It's based on the conditional probability. I would like that you think about, from a human perspective, you think about this problem. Imagine we have a 50-year-old person that has gotten a positive COVID-19 result after a PCR test. The question is, what is the probability that this person is infected by the COVID-19, knowing that he got a positive test of PCR? Which kind of information do we have? We have the prevalence is 1% for this kind of people in this region. The test has a 90% of detection rate, and the test has a 10% of the false positive rate. What do you think? What do you think? Do you think that the probability that this guy is infected or not being a positive test? Well, the conditional probability, this is the formula that is very old. Well, if you apply that, you will see that the probability of having COVID-19 in real being positive in the test is just very small, only the 7%. Why? Because we have a high false positive rate. Okay, well, we have AI algorithms that works in this way, but with massive data. Imagine that you can apply this algorithm that is very logic. You can apply this algorithm based on this conditional probability using software, power computing. You can identify this kind of conditional probabilities and find very weird results that you couldn't imagine before. This is the secret of AI using statistics. So when I were mentioning statistics, is because that we are using more of the times classical statistics, but the difference is that we are using these statistics with a lot of data and a lot of iterations. And this is a map of the main or the most famous algorithms based on the Bayesian classification and decision trees. Well, I won't go in detail, but could you see we have many algorithms, and for each algorithm we have a score. Usually we have the triple of scores in order to measure the validity of an algorithm when we have a model. So many scores for many algorithms, but this is a mess. So there are many options. So how to proceed? In pharma, we're lucky. In pharma, we have this formula, the confusion matrix. This matrix is a very good way to measure the validity of a model and has been accepted around the world, everywhere by the pharma community, because it was introduced in the chemometrics, and also was introduced several times by the FDA when they were announced the process validation process in 2014. If you can read the process validation guidance from the FDA, you will read that this confusion matrix can be used for everything, and it's very good. So, although you have many scores in order to validate a model, please, if you want to go to life science in front of the authorities, try to think first in the confusion matrix. Well, this is the how good is the accuracy of different models when you go to when you work with deep learning, when you go with naive Bayesian networks, and so on. It's just for curiosity. It's important to mention that the accuracy is higher with deep learning. The problem with deep learning is that you need a lot of data. This is the only problem. And I would like to bring to you some real examples. Let me start first with the AlphaGo example. Probably, I don't know if you know AlphaGo, but I like this example because it's learning the rules by playing the game. So AlphaGo is a computer program that plays the board game Go. It was developed by DeepMind Technologies, which was later acquired by Google. Why Google acquired this company of games? Well, in October 2015, the original AlphaGo became the first computer Go program to beat a human professional Go player. AlphaGo and its successors use a Monte Carlo tree search algorithm, and the most amazing thing is that the program learned the rules playing the game. So no one was programming the rules. Here, I'm very proud to bring this real use case with Novo Nordisk. You can see me here in this picture. I was really young. Well, in this case with Novo Nordisk, this is a public case that we can diffuse because Novo Nordisk was announced that publicly, about how AI in action can work discovering the root cause problems in a packaging line in order to improve the overall efficient equipment. The problem was the following one. They had this packaging line that was so critical because they were preparing the manufacturing the drugs based on an insulin product that is distributed around the world, and they have contracts everywhere. Well, the thing is that this highly automated packaging line suffered a lot of downtimes. They didn't know why, and because they were including some parameters in the packaging line, like speed, like batch size, like many. So, well, they couldn't know which is the problem. Well, the thing is that we add in the problem values like, for example, temperature, humidity. We took all the values coming from the PLCs. We put in the platform also the shifts and a lot of information. Well, after 8 weeks working with this packaging line, taking data in real time, breaking silos of data, we got this kind of data. The OEE, the overall equipment efficient value that they were expecting was the blue line, but they couldn't achieve this efficient, and they didn't know why. Putting all these kind of concepts, all of these variables, and we were working with 130 factors, 130 variables, and 2,500 batches in 8 weeks, and we're controlling these critical variables, we were able to predict this OEE. The black line is the OEE predicted, and the green one is the real one. Could you see that they are so close? Why? Because we included variables like temperature, humidity, pens per cartoon that they were creating, the size of the batch, and the day of the year. Could you see? Who can think that the day of the year could affect my production? So this is crucial because the day of the year brings metadata like humidity, temperature, and this kind of characteristics. So could you see how much important are metadata? This is a very good example in order to see how AI can work in action. This is the other example coming from the CPV of the future that I mentioned before, that we are working with the Product Quality Research Institute and the PDA. This is the metabolism of the Pichia pastoris, very, very complex. And Pichia pastoris is used in food, but also in drug. Well, the thing is that how we can ensure that every single batch we produce is good. Well, we put all the sensors in this bioreactor, 5 liters bioreactor, and we try to figure out which factors were the most important. Well, we applied design of experiments and we applied AI. The first thing that we did was to identify the variables that were explaining the real problem. So not everything is always needed. Sometimes you need only those variables that they are the most relevant to explain the problem. Taking these variables and define which of them they explain the problem, you can create models, and we created 1 model per hour, and the fermentation spent required 24 hours. So we had 24 models, 1 per hour. And we identified that the room conditions, I don't know if you can see here well, but the room conditions were affecting to the methanol production. That was so crucial because no one, and they are really experts on that. Could you imagine? They are professors at the university. They are really good. We have companies like GlaxoSmithKline, like Sanofi, working on that. Room conditions were affecting to the methanol production. So depending on how the heater is switched off in the laboratory, that could affect the process. And we created this fingerprint explaining the batch. Nowadays, we can produce lipas, and specific lipas coming from the Pichia pastoris fermentation, in order to produce drugs, always having the optimal batch, depending on which is the characteristic of the raw material that we are using. So the only thing that we have to do is, create an AI model and be sure that the variables condensed in just a few dimensions, principal components in this case, are following this fingerprint. This fingerprint is like a trajectory in physics. We don't know what does it mean. We don't know which is the y-axis or the x-axis. They are just mathematical dimensions, but they are condensing CO2, agitation speed, O2, glucose, methanol, all of them, they are condensed in these new dimensions. And I would like to bring another use case, a real use case. I like this case because do you know the history of House of Cards? This is a series coming from Netflix. Well, I like to mention that because this is the best example of right at the first time. Let me explain you that Netflix 1.0 started in 2007 asking for the customers' opinions through the red envelopes of the DVDs that they were sharing, rating the content in the 1 to 5 score. Therefore, Netflix algorithms were fed with the most sinister sex and corruption content than their customers requested in the surveys. The same year that House of Cards premiered, HBO, the competitors of Netflix, commissioned 130 pilots with a cost about $400 million. Well, Netflix was right at the first time, okay? Because they believed in the data coming from the analysis that they did using AI. Well, the same example can be applied in this real example coming from a company. Is one of the top 5 pharma companies dedicated to the human plasma. This company is getting plasma coming from donors around the world, and they produce blood drugs based on this human plasma. Well, the thing is that this company didn't know why systematically, year, the yield of the final product that they are producing were going down. So the yield were decreasing, and they didn't know why. And even worse, they didn't know how to improve, how to solve the problem. Well, could you imagine the difficulty? When you work in drug manufacturing, you can more or less control the raw material that's coming from your suppliers. But could you imagine how much difficult it is to control the plasma, the blood coming from donors around the world? This is so difficult. Well, we detected using AI, first, which were the critical operations in the drug manufacturing based in blood that were more critical in order to get the expected yield. That was the first thing, and this is a very good practice. Please try to figure out which is the most important variables explaining the problem. First thing. Second thing, once we did that, we tried to figure out the root cause. So making a supervised algorithms, and now which were the best batches, the wrong and the bad batches, we classify them and we analyze when these batches were good and when these batches were wrong. And we identified the raw materials that were coming from a specific state of the United States that were affecting to the yield of the product. Well, curious. I cannot reveal the names, but it's curious to know that there were an area, a specific area that was contaminating or that was decreasing the final yield. But this is not all. The good thing is that identifying the critical variables and relating the critical material attributes coming from donors with the critical process parameters and the critical quality attributes that we are waiting at the end of the process, we created several models, more than 24. I can believe me, a lot of AI models for every single phase of the process in order to set up the values of the equipments to the optimal values, for example, filtering, for example, ultrafiltrating, for example, for ultrafuge processes, in order to determine how to get the optimal value. Nowadays, the raw material or the yield of the batch is more independent from the raw material. Okay, so we had good results. So this is some examples. And summarizing, this is how AI works in life science. This is coming from IBM. So it's important to define first the problem, understand the problem, and having good data, build and choose which is the algorithm that you want to work with. And please, when you work, you have to monitorize the results that you are getting continuously, because probably new parameters, new variables that you have not considered at the beginning must be considered after some iterations. Well, just to finalize, AI in the real life, this news is coming from the New York Times 2 years ago. It seems that the US wants to regulate AI 2 years ago. In life science, I think that I already mentioned that the European Pharmacopoeia, that is the Bible for Europe, was announced in 2017 to AI algorithms as valid chemometric methods to be used in pharma. The FDA is proposing AI as medical devices. The FDA is having things like computational modeling, that at the end is AI, big data, as part of their priorities. The European Commission 2020 they wrote a white paper based on how artificial intelligence is bringing value to the society.